physical chemistry could be divided into four broad areas, and these are actually chemical thermodynamics, statistical mechanics, quantum mechanics, and the kinetics. And this thermodynamics deals with these macroscopic properties like pressure, temperature, mole number, volume, which are observables and could be determined by means of certain instruments. And the thermodynamics is a part of this classical mechanics. And on the other hand, quantum mechanics deals with the motions of the molecules, electrons, nuclei, etc. And the classical mechanics cannot explain the behavior of such type of microscopic properties of the system at this molecular level. So the statistical mechanics makes a bridge between this quantum mechanics and the thermodynamics. This makes a bridge, and the thermodynamical macroscopic properties are explained on the microscopic properties obtained from this molecular motions in the quantum mechanics. So this one makes a bridge between these two. And the last fourth one, the kinetics. Kinetics is the rate processes such as the chemical reactions and the transport phenomena, means transport of mass from one place to another, which is called the mass diffusion. Transport of kinetic energy from one place to another is called the thermal conductance. Transport of charge we call the electrical conductance, and etc. So these four chapters total constitutes this physical chemistry. So to my turn, from today onwards, I shall discuss this thermodynamics. Actually, thermodynamics is a very important chapter in basic science, especially in physics. And the laws of thermodynamics in physics could be applied in chemical reactions and for the explanations of this chemical phenomena. And so this part of this thermodynamics we call the chemical thermodynamics. And in the discussions of the chemical thermodynamics, today in lecture 1, I shall start the introduction only. Thermodynamics is consisting of these two parts. One is thermo. Thermo means heat, and it is the dynamics means motions of this piston in this engine for doing this mechanical work. So this part is the mechanical one. So this thermodynamics quantitatively relates between the heat and mechanical work. The thermodynamics contains 4 laws in total. First law, which is the conservation of energy, means energy can neither be created nor be destroyed. It could be transformed from one form to this another. If heat is converted into work, then equivalent amount of heat will be, if heat is disappeared, then equivalent amount of work will be produced. This second law puts a limit for the conversion of heat into work, and this second law is much more important. And the third law provides the method to determine the absolute values of some thermodynamical properties, especially the entropy, which is most important thermodynamical property in our chemistry. And the fourth one, which is called the zeroth law, it comes much later, and it defines the temperature and also provides this method how to measure the temperature by the use of this thermometer. This thermodynamics is applied to the system at equilibrium, and to the system at equilibrium means the pressure, temperature, composition all will remain time independent. And so this thermodynamics does not concern with this time variables. For the whole thermodynamics, the time variable is totally absent. And not only that, the thermodynamics does not consider the constituent particles of this system, whether this system is composed of molecules, atoms, electrons, anything, or the colloidal particles. Thermodynamics does not bother about the constituent particles of this system. It measures only the temperature, pressure, volume, mole number, etc. So thermodynamics is having a much more predicting value, and this predicting value means whether a process, either physical or chemical, whether the process is feasible or not, whether the process will occur or not, that could be decided by the thermodynamics. Actually, thermodynamics predict whether this process will occur or not. Suppose for this example, I may consider one reaction, say nitrogen gas, very simple Haber's process, 3 hydrogen gas, and sign of reversibility, twice ammonia gas, formation of ammonia from its constituent elements. This is the very cheapest way to produce this ammonia, but the first question comes whether the nitrogen will combine with the hydrogen or not. This is the first criteria. If the thermodynamics gives a green signal that the nitrogen will combine with the hydrogen, then a chemist will try to innovate a suitable catalyst to accelerate the rate of this reaction so that this equilibrium will be attained at much quicker time, and they will also choose the temperatures, pressures, experimental conditions so that the yield of ammonia becomes maximum. So before, these are the introductions. Before proceeding the main first law of thermodynamics, I shall discuss some terms which are very much used in the thermodynamical chapters. And this first term commonly used terms in thermodynamics, in chemical thermodynamics. First one I can call the system and surrounding. System and surrounding. system is a part of this universe. System, suppose this is system. System is a part of this universe selected from this thermodynamical study. It is separated from the rest of this universe by a definite boundary, maybe a real boundary or maybe imaginary boundary. And this rest part of this universe is called the surrounding. Surroundings. So system, the rest part is surrounding, and so the system plus surroundings gives this universe. And system could be divided into several types depending on some properties. System, say first we can call this system could be divided into two types. One is homogeneous and other is heterogeneous. Heterogeneous. In case of homogeneous systems, every part of the system is uniform. All the properties of this system is uniform at every part of the system. It may be the mixture of gases, mixture of immiscible liquids, or some pure solid. They will constitute the homogeneous systems, and it is the one-phasic system. And in case of heterogeneous, every part of this system is not uniform. Say liquid in contact with this vapor, or a mixture of immiscible liquids which are not miscible to each other, or the mixture of pure solids. Each solid constitutes one phase. So it is the multi-phase systems. More than this system, this heterogeneous system contains more than one phase. But in thermodynamics, the classification better we express on the nature of this wall, nature of the walls or boundary which encompass this system, which separates the system from this universe. And first one is the open system. The second one is the closed system, and the third one is the isolated system. In case of open system, say the mass and the energy could be freely exchanged between this system and surrounding. Means and mass and the energy are not fixed for that system. So we can give one example. Say here is the liquid, and Bunsen burner is applied to heat this one, and it is vaporized. So in this case, this is the imaginary boundary. This vapor is diffused to these surroundings, and in this case, these walls are called permeable wall. Permeable wall means through this wall, the energy and this energy and mass can be freely exchanged between the system and the surrounding. This is surrounding. So in this case, the interaction of the system with the surrounding is maximum. Intense interaction is there. Any effect of the surroundings certainly will affect the open system. Human body, for example, is a best example of this open system. So keep this human body well, we shall have to keep this surrounding quite well. And this one closed system. Closed system means these materials of the system is totally closed by this definite boundaries, and this for this closed systems mass is totally conserved, but energy could be exchanged between the system and surrounding. For example, I can say one bottle, one cork bottle, hot water bottle, here hot water is there, and it is made of glass, and here it is corked out, and this wall is called dithermal wall. And in the case of dithermal wall, the mass cannot, energy can go freely in between the system and this surroundings. But this energy mass, but this mass is restricted. Mass is not allowed to exchange between the system and the surrounding, but the energy could be freely exchanged. And the last one is isolated system. Isolated system means this is the closed systems, and it is insulated. It is wrapped by this insulator, by proper insulator, like this polyurethane foam. Polyurethane foam, one insulator can be wrapped here. Better the quality of the insulator, better would be the properties of this isolated system reveals. And here it is the suppose hot water or any hot liquid, and in this case this mass, this is energy and mass, both are not permitted. Energy and mass both are not permitted to exchange between these systems and surrounding. Here mass and energy both are concerned. Here it is the surrounding. So there is no impact, there is no interaction between the isolated system on this surroundings. If you change this surroundings, so this isolated system remains intact. And now the second one, the second term, which is also very popular, is the property this is second one, property of the system. The system may have different properties: volume, temperature, pressure, mass, and the heat capacity, density, refractive index, viscosity, surface tension, and so on. But all these properties could be divided into two types. One is extensive. Extensive property, extensive in nature, and other is intensive in nature. Extensive means dependent on the amount of materials in the system. It does not depend how much this material, it depends actually. This extensive property are those which depends on this amount of this materials present in this system. Suppose volume, mass, heat capacity. Heat capacity means amount of heat required to increase this temperature of the substance by 1 degree. If the amount of this mass, amount of the substance is increased, then heat capacity of that substance will also increase. And here the 5, we shall discuss later on, 5 thermodynamical properties. They are very important, and these 5 thermodynamical properties say internal energy, denoted by U, and this enthalpy, denoted by H, and the most important one is entropy, denoted by S. Free energy, bracket, denoted by G, and this work function, denoted by A. So these are the extensive properties. All of these of all these properties depends on this amount of this material. And intensive means independent of the mass or the amount of material present in the system. And to memorize this one, here independent, intensive means independent of this amount of material. So this IN is common in both the cases. And it is suppose the molar volume means volume per mole of the substance, and the pressure, temperature, specific heat, and molar thermodynamical properties, molar thermodynamical properties. Not only I can say the refractive index, viscosity, surface tension, these are all intensive properties. In order to now one, so intensive property, intensive means independent of the amount of this material present in the system. So these are the examples of these properties of the system. And one way to distinguish between this intensive and extensive, let us consider this pressure, which is very puzzling to classify this one. Suppose here some gas, say 1 mole gas is present, and this pressure, this gas gives this pressure a P. If we divide this system into 2 halves, then here is the half mole, and here also half mole gas present at each chamber. But whatever the amount of this material present in each chamber, this pressure, this is also the pressure P, and this is also the pressure P equal to the original value. So this pressure does not depend on the amount of this material. So pressure is intensive. The next third one, the state of the system. In order to define the state or the condition in which the system is existing, we use the four state variables. Four state variables: pressure, and the temperature, and the volume, and the mole number. These are the properties, these are the state variables which are used to define the state of this system. But for closed and the isolated system, this n is fixed. So n is kept fixed and a is no longer a variable. So we are having this three variables: pressure, temperature, and volume. These three variables are again connected by an equation. Suppose for ideal gas, this equation is PV equal to A RT. Since one equation is there, N is constant for this closed and isolated systems. R is constant. R is also constant, fixed as it is the constant. And so PVT, these three are connected by an equation. So three variables, and there is one equation means one restriction. So two variables we can change independently. If we change this pressure volume, then temperature will be automatically fixed, will be given by this equation. If we change this pressure and temperature according to our own choice independently, then V is fixed and so on. So state of a system, state of this closed and isolated systems, this is expressed in terms of the pressure volume, or another set is the temperature volume, or the temperature and pressure. And the third one need not be required to specify, as the third one is obtained from these suitable equations of these three variables. So these when any change of this variable, any change of the variable means the system has changed its state. And if we bring back the system to its original state, then the variables will have to bring to its original values. And what is very interesting for any system, if say pressure and volume are fixed, then any property, say density, diffraction index, viscosity, surface tension, whatever may be the other properties, they will also remain fixed. If we keep T and V fixed, then also all the properties, thermodynamical properties, all properties will remain fixed. This is a very surprising phenomenon. So the fourth one, path of the system. Whenever the system moves from one state to other state, it will follow a definite path. Path is the sequence of these intermediate steps arranged in order. Say one example, I can say system is defined by this pressure and volume. This is the pressure and this is the volume, and suppose this is the initial state, and here the pressure P1 and volume V1, and it is the final state, and it is the pressure P2 and volume V. And this system can come up from initial state to final state. Suppose this path, and suppose this is path number 1, or it may also come to this path, and this is path 2. This is path 2. So these are the paths for the system to come up from this initial state to the final state. And the fifth one the thermodynamical equilibrium. Thermodynamical equilibrium. When the system is having the temperature, means mechanical temperature is fixed, temperature, pressure and the composition fixed, does not change with time, we call the system attains thermodynamical equilibrium. Temperature fixed means thermal equilibrium attains, pressure fixed means mechanical equilibrium is attained, and composition fixed means chemical equilibrium is fixed. Whenever a system attains this thermal equilibrium, mechanical equilibrium and chemical equilibrium, the system is said to attain the thermodynamical equilibrium. There is a little bit difference between this equilibrium and the steady state. For say A, for isolated system, when temperature, pressure and the composition are time independent, means fixed. It is this isolated system is at the thermodynamical equilibrium. And in case and another criteria for non-isolated system, another non-isolated system. This system means isolated system means walls are adiabatic walls. This is non-isolated system means walls are dithermal walls. And for non-isolated system, one condition is that the temperature, pressure and composition is fixed. One condition. And second condition is that if this non-isolated system is separated, if the system is separated from surrounding or removed from the surrounding, then if P and composition remain unchanged, it is called the thermodynamical equilibrium. Non-isolated system attains thermodynamical equilibrium if the temperature, pressure, composition is fixed, and if the system is removed from the surroundings, then also if these three remains unchanged, then it is also the thermodynamic equilibrium is attained by the non-isolated system. If one is obeyed but two is not obeyed, then the system we call in steady state for these non-isolated systems. This sixth one, and this sixth is the process. Process is very important. Process means the operation. Process means the operation by which the system changes its state from initial state to the final state, and the operation is known as the process. And a process will be of a different types. Say first one is say cyclic process. If the system moving in different states and then again coming back to its initial state, then the process or the operation is called the cyclic process. As you can say from here to here, it is coming in this way, and if it also goes to this way and coming to here, then these two states together we call the cyclic process. So second one, in case of cyclic process, the state variables remains fixed. Temperature, pressure, or the volume, all will remain fixed whenever it comes to its original state. And 2 is the isothermal process. Isothermal process. In this case of isothermal process, T remains fixed for the whole operation of this system. And whenever the temperature is kept fixed, the walls are dithermal walls and heat exchange will continue. And this third one is adiabatic process. The walls are made up, the walls of the system are made up these adiabatic walls and isolated systems. In the heat exchange is not permitted, their temperature must rise. Temperature changes. And the fourth one, isobaric process. In case of isobaric process, P remains fixed and volume will automatically change. And the fifth one, isochoric process. Here V is fixed and P is changed. And the sixth is the isotropic process. Isotropic process. Here the heat capacity remains fixed during this operation. The last two operations we will consider this seventh reversible process. Reversible process. This is a very important process. Reversible process. In this case, all we know, whenever any change occurs, anywhere, two forces are there. One is driving force, which is making this change, and the other is opposing force, which will try to oppose the change. And so in this, whenever the driving force and opposing force are different, their difference of this driving force and opposing force are very, very small, infinitesimally small. We call this process is reversible process. This is a very slow process, and this process infinite time required to effect this change, and this is not a real process, it is a concept. And we can cite our example, say expansion of this gas. Expansion of a gas. Expansion of a gas. Suppose the piston is here at this position A, and volume V1. And here the piston means this piston is weightless, frictionless, and movable. And this piston is movable and weightless, frictionless. So here it is, if this pressure of this gas is P1, then this is also P1. This is internal pressure, this is the external pressure, this is the opposing pressure, driving pressure, this is the opposing pressure. Suppose we like to have a change from this volume V1 to V2. Volume V1 to V2 of this gas. Say N moles gas. N moles gas. Then how the V1 to V2 change occurs? This change we like to decrease this pressure P1 to P1 minus dP. That means a very small amount of external pressure is decreased. Then this one is the driving force. This driving force will lift the piston to a small volume change until this external pressure becomes also equal to internal pressure becomes equal to P1 minus dP. So there is a small volume change, and the system at this step, this system again attains equilibrium. And from this to this, again suppose P1 minus 2 dP. dp is very small. dp is infinitesimal small that tends to 0. Means that if we lower down this value of dp, then there will be no change. And when for this second step, again the piston will move to a certain height, and this one multi-step. And lastly, it is a P2. Volume changes from P1 to P2. And this again, this P2 plus dp, and by this multi-step, this will be volume change occurs, and ultimately the volume changes from P1 to P2 by an infinite number of steps, and each step this system attains equilibrium. And so this is why the reversible process is also called the equilibrium process. And you know, I shall show later on, the system, if the system brings back to its initial state, then no help of this external agency is required. The system comes back to its initial state without without the aid of external agency. That would be shown later on. And in this case, this drawing of this graph, say suppose this is part 1, these are the intermediate steps. Only for this reversible process, this sort of plot or this sort of curve we can draw. And the last one is the irreversible process, not reversible. Irreversible process means this criteria, whenever for a process this criteria is not obeyed, not maintained, it is called the irreversible process. Suppose in this case, here it is V1 and pressure is P1, here also P1, and at a single step P1 to the P1 is decreased to P2, and volume suddenly rises from V1 to V2. So this process is spontaneous, and this process is sudden process. This process is one-step process, and in the intermediate, no equilibrium is attained, and this sort of graph we cannot draw. In this case, what will be the graph? Here P and here V. This is the initial state. P1 V1, and it is P2 V. We do not know the intermediate steps from here to here, coming from here to here, and so this sort of graph could not be drawn for this irreversible process. Irreversible process is a real process. And then the seventh one, and the seventh terms, and this is seventh one, perfectly a differential quantity. Say X means which quantity or property could be differentiated and which are not differentiated, could not be differentiated. And the criteria for perfectly differential quantity is that one, this X is state function and single value. Say P is single value, means from here initial state, this is P1 is the pressure and volume of this initial state. This is single value, and this defines this initial state, this defines the final state, and so on. And this for this two, second criteria, dx means x of final state, the value of x in the final state, value of the x in the initial state. These two equal to fixed means independent of this path. Is independent of path. Whether the system comes to this way by the path 1 or whether the system comes to by the path 2, this P1, P2 minus P1 or V2 minus V1, they will remain unchanged and does not depend on this nature of this path. And this third one for this cyclic integral means this change of x for the cyclic process equal to 0 for cyclic process. If the system comes from this to this and here it is this, then P1 V1 will have the same initial value and change of P, change of pressure, change of volume will be 0. And the fourth one, which is very important, Euler's theorem. Mathematician Euler's reciprocal relation. Reciprocal relation. This relation is that suppose x is a function of a temperature and a pressure. Then del 2x divided by del p equal to del 2x divided by del p. Means irrespective of the differentiation, the value of each term, each side will be the same. And if this condition is obeyed by this x will be a perfectly differential quantity. We can verify this one. Suppose for ideal gas, P 1 mole ideal gas, PV equal to RT. For 1 mole ideal gas. If we like to verify this one, then suppose we like to verify whether the P is perfectly differential or not. Then P equal to RT by P. Then we calculate del 2P divided by del V del P. First differentiate with respect to T, keeping V constant, and then differentiating with respect to V, keeping T constant. And this one equal to del 2 becomes equal to del P by del P. You can do it in your home and can verify whether the both sides will be the same or not. If the both sides become same, then P is a perfectly differential quantity. This is all about the introduction of the thermodynamics and very preliminary discussions. And from next lecture, I shall explain the first law of thermodynamics.